And we are on to lesson 2 in activity 2, working with geometric series today. So our first learning target is going to be to derive the formula for the sum of the finite geometric series. And then we're also going to calculate the partial sums of a geometric series. I'm going to start with some math terms that we see along the side just to review those. The first one is finite series. And a finite series is the sum of a finite sequence and has a specific number of terms. That means the sequence has a last term to it. Okay, so our infinite series, however, is the sum of an infinite sequence and has an infinite number of terms. And later on in this lesson, not right away, but later on in this lesson, we're going to look at the infinite sum and an infinite series. Okay, so we're going to get to doing the derivation of the geometric sum formula. Now, it looks a little tricky, it looks a little messy, but remember the biggest part of the lesson is you being able to apply this formula, but I'll talk you through deriving it as well. So let's review a geometric series. I know it looks a little messy right here, this S sub n. So a sub 1, of course, is the first term. Then the second term is found by taking the common ratio times that first term. And you continue that to get to the third term and the fourth term and so on. Okay, now, right here in the middle is where they're going to end up giving us the formula, and then they're going to show us how to get it. So there it is right there. That's how we find the sum of a finite geometric series. Okay, and so we read that as a sub 1 times the quantity, and then the numerator 1 minus r to the n power divided by 1 minus r. Remember, r is the common ratio. So question number 1 just walks us through the steps of doing that, so I'll kind of talk you through that a little bit. To derive the formula, step 1 is going to require multiplying the equation of the sum by negative r. So basically what they did is they multiplied both sides by negative r. So there's your series, and then here is the times negative r on both sides. And so you can see that sort of changed a few of the signs in there. It changed all the signs actually to negative. So what they have us do next is combine terms on each side of the equation. And so when you start combining terms, basically what you're doing is you're adding the two expressions together. And when you do that, you get the S sub n plus negative r S sub n, or in other words, it's really S sub n minus r S sub n. Okay, so that's what you get on the left side. On the right side, you're going to see that almost everything cancels out. You have positive, a sub 1 r squared and negative a sub 1 r squared, positive a sub 1 r and negative a sub 1 r. So when everything cancels out, you're left with that first term, a sub 1, and then you also, in the end, will be left with the minus a sub 1 r to the n. Okay, and then basically, like everything else just has a buddy, cancels out, everything else cancels out, and you're just left with that. So the next step says to factor out the S sub n on the left. So you can see that both terms on the left have S sub n. So I'm going to pull that out. So S sub n comes out. Well, when you factor S sub n from itself, you got to put a 1 there to hold its place. Minus r still equals a sub 1 minus a sub 1 r to the n. But notice we can also factor out the a sub 1 on that side. So a sub 1 comes out, and you get 1 minus r to the n. Now it looks a little bit more like that formula. We're just going to do a divide to get the s sub n by itself. So I'm going to divide both sides by the 1 minus r, so that s sub n is alone. So I'm going to have a sub 1 times 1 minus r to the n, all divided by 1 minus r. And that is our formula for our sum. One other thing on the side here, we have a math tip. It says when writing out a sequence, separate the terms with commas. Okay, so we see that in 2-1, we saw that in 1-1. When you get to a series, however, in a series, we're written out as the expression separated by addition symbols. And if a series has negative terms, then the series may be written with subtraction symbols. So that's how you know if you're working with a sequence or if you're working with a series. All right, now our next problem, we have an example here where they kind of show you how to take the terms and find the ratio and plug in. So you can, of course, read that on your own time, but I want to practice some with you. So we're going to go to the next page where we have some try these problems. And the try these problems, they don't give you a lot of space to work. So I'm going to work kind of above and around to do the examples for you, just to show you. All right, so hopefully you have the formula handy and you're able to, let's look at the part A. You're able to find the S sub 5 for the geometric series. So in part A, they tell us A sub 1, and they also tell us R, which is good. So that should give us everything we need. So if I write my formula down, so I'm going to put that up here just so I can keep track of it. So remember, S sub n is equal to A sub 1 times quantity 1 minus r to the n over 1 minus r. So for part A, I want S sub 5. So I'm going to do that. Let's change colors so we keep track of what we're doing. We'll go to blue. So S sub n, I want S sub 5. So the first term they gave us is 5. And then they give us the common ratio. So they gave us everything we need. We just have to practice the calculation part. So 1 minus 2 to the 5th power, because 5 is our n. Oops, back to there. 5 is our n. And then divided by 1 minus 2. So what you're going to need to do is just practice plugging this into your calculator. And remember to use order of operations. Okay, so you can plug in, 1 minus 2 to the 5th. 1 minus 2 is -1. And then the last thing you would do would be to multiply all of that by the 5. So you do want to practice doing that. Once you do that, you should come up with 155. So if you're not coming up with S sub 5 equals 155, then we'll practice that in class so that I can kind of figure out what you're doing on your calculator, what your order of operations looks like. Okay, so that's just us first just plugging things in, and they gave us everything we know. Now for part B, which I'll use the space probably next to it. I might have to move for part C, but for part B I can use the spot next to it. And again, they're telling us, they want us to find S sub 6. Okay, so I want S sub 6. And looks like I'm ready to go. I've got A sub 1, which is 256. But they didn't give me my ratio. That's not a problem, however. I should be able to find it. I know that I have to divide the terms, so if I do 4 divided by 16, I get 1/4. So my ratio is a little messy this time. It's going to be 1/4. So 1 minus r, which is 1/4, taken to the 6th power, and then divided by 1 minus 1/4. So again, it's pretty messy. So you definitely want to practice plugging things into the calculator, using parentheses, and so on. Okay, so once you're done calculating all that, you should come up with 341.25 for part B's answer. Okay. So play around with it a little bit, practice, and let me know. Sometimes it's easier if you change the 1/4 to 0.25. If you can change the fraction to a decimal, sometimes that's easier to get it into the calculator. So just let me know if you have any questions on that. Okay, now part C, we haven't seen the sigma notation yet, but I do want to show you how to do that one because basically it's really just plugging in numbers. And so let me go back to green for a minute. So the sigma notation, that represents a sum, okay? And they kind of explain that over here on the side in the math tip. So let's go there first, actually. It says, recall that a sigma notation is shorthand notation for a series. So when they give you something like that, you can see it's geometric because I see like a times 2 to the n minus 1 power. So basically what that means is you want to go from 1 to 3. Those are your terms. So you're going to be doing like 3 terms there. And they, if n is 1, you plug in 1 for n. If n, then you have to plug in 2 for n, and then you have to plug in 3 for n. So you could get all 3 terms and just add them up. Okay, you could do that for sure. But part C actually has, it's a little different. It's got terms 1 to 10, and I don't want to plug in all those numbers and then add all those numbers together. So instead, I'm going to plug in to find the first number, and then I'm going to plug in to find the 10th number. And then that'll help me find, because I know I need those things, so then I can find my sum of my first 10 terms. So let me go ahead and find the first term. So let's start with that. So the first term would be found by plugging 1 in for n, which is pretty easy. So if n is 1, it's 2 times 3 to the 1 minus 1 power. And you should remember from last year that that's 2 times 3 to the 0 power, which is 2 times 1, or 2. So our first term is 2. So a sub 1 is 2. Okay. Now, the ratio we can actually see we should be able to see like right in the problem. So our common ratio is 3. That's always going to be the base of the exponent. And so the common ratio is 3. And I guess I really don't need to get that 10th term. I probably don't. I think I did on my handout, but no, really we have everything we need right now. So to calculate, all we have to do is plug into the formula. So I'm actually going to move down towards the bottom now to do that because I've got more room down here. So formula again, if you remember, is S sub n equals a sub 1 times quantity 1 minus r to the n over 1 minus r. Okay. And I might change to black just so we can see it a little better. All right, so we figured out our first term was 2. So a sub 1 is 2. So S sub, we want to know 10, sum of the first 10 numbers. A sub 1 is going to be 2, and our ratio is 3. So 1 minus 3 to the 10th over 1 minus 3. Okay. So again, order of operations, you have to do 3 to the 10th, 1 minus 3 to the 10th, divide by negative 2, which would be 1 minus 3, then times 2 in the end. So the sum of the first 10 series, if you calculate correctly, is actually pretty big. It is 59,048. Okay, so we'll work on some more of those when we get into class, and you guys have some questions on that, I'm sure. All right, so take a little breath. And what we're going to move on to next is talking about an infinite series, and what that looks like. So they actually have kind of a neat little problem they talk about here with an infinite series. So if you have a piece of paper handy, a Post-it note or just a blank sheet of paper, it doesn't have to be a square. They actually start with a square piece of paper, but it could be anything. So if we, let's go ahead and start with the beginning of the problem. It says, recall the sum of the first n terms of a series is a partial sum. That's what we were doing up there in the try these. We were doing the sum of the first 6 terms or the first 5 terms. So that's considered a partial sum. Okay. For a geometric series, partial sums, S sub 1, S sub 2, S sub 3, S sub 4, they form a sequence with terms that approach a limiting value. Okay, so like our answers that we got in those problems. And the limiting value is called the sum of the infinite geometric series. So we're going to start working on some infinite series problems, but just to get the idea of what an infinite sum would be, something similar, they ask us to start with a square piece of paper. So I'm going to take a Post-it note. You'll hopefully be able to hear me do the tearing. And it says, let it represent one whole unit. And it says, cut the paper in half. So take my scissors, and I'm actually going to cut the paper in half. And it says, leave one piece of paper on your desk and keep the other piece of paper in your hand. Now the paper on your desk represents the first partial sum, S sub 1 equals 1/2. Okay, so we've got S sub 1 equals 1/2. That's our first sum right there. Okay, then it says to cut the paper in your hand in half again. Okay, so I'm just going to tear it. Okay, and the paper on my desk now represents the second partial sum. Okay, which is going to be the 1/2 plus, think about it, it would have to be 1/4 now. Okay, so now I'm going to tear the paper again, and it says do this as many times as you can, and eventually, the paper is going to be just too small to tear. Okay, so you do it as many times as you can, and what's happening is, you're always having the pile on the desk is getting bigger, and the paper in your hand is getting smaller. Okay, so when you get to question number 4, we can think about this now in terms of fractions and in terms of sums. Okay, so like S sub 1, that was that 1/2. That was the first sum. Well, then we tore the paper again. And so then it was 1/2 plus 1/4. Okay, and then when we add those together, we actually get 3/4. Okay, so kind of getting back closer to that whole. Okay, well, then we tore the paper again. So we were adding the 1/2 with the 1/4, but then adding a 1/8 to it. Okay, and that actually, when you do that math, if you remember common denominators and all that fun stuff, you actually get 7/8. That's even closer to 1. So that pile on your desk is getting closer and closer to a full sheet of paper, the original sheet of paper that you started with. Okay, so again, we could, keep doing this, but the fractions start getting bigger. Let's just fill in S sub 6. So that was going to be the 1/4 plus the 1/8, and then next we're adding the 1/16 of the paper, 1/32, and we just keep cutting the paper in half. So we're multiplying that ratio, and when you add all that together, you actually get 63 out of 64. So you're getting really, really close to 1, and that's what we call a limiting value. So the limiting value is actually appears to be 1. So I'm gonna put that in part D now, because we've actually answered that question when it says, do the partial sums appear to be approaching a limiting value? And I would say yes, the limiting value appears to be 1. Okay, if we could keep tearing that paper and keep adding, we'll get closer and closer and closer to 1. And so what they wanted us to do is to plot the first 6 partial sums together. So if we were, gonna do that, we would have down here the first time we cut, second, third, fourth, fifth, and sixth. And as we did that, it started up, at 1/2. And so, I mean, the Y value numbers are going to be pretty small. So I would probably go by tenths for that. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, something like that. And maybe even get 0.9 up there. And so what happens is, as we tore the first time, we were up here at 0.5. The second time we tore, we got 3/4, so that was 0.75. So I mean, that jumped up to here. And then the third time it was 7/8. And so, if you think about changing these numbers to decimals, if I do 7/8, it gets closer to 1, it's 0.875. So I mean, that's getting us even closer. But then, as we continue on, let's say 63 out of 64, that's going to give me 0.98. So I mean, we're going to be getting closer and closer and closer to 1, and it also follows that curve sequence again, like you saw that shape when we looked at the geometric. Okay, so that's what a limiting value is. So on our next page, we're going to talk a little bit more about whether or not we have a limiting value. And so looking at the difference between when we do and when we don't. And I'm going to try to shorten this up a little bit, because I know the video is getting a little long. So let's look at the sequence. So the first 5 partial sums for this sequence, it says, list them. So the first sum, S sub 1, well, that's just 2. But if I add the 2 with its 4, its second term, well, now I get 6. And if I keep doing that now, if I now want to add the next term, now I have to add it to the 8, well, now I get 14. You should hopefully see what's happening. We're just going to continue to grow and grow and grow. If I add the 4th term to it, now I've got 30. And if I add the 5th term to it, well, now I'm up to 62. Okay, so we're not really approaching any number. We're just going to continue to grow. So there is going to be no limiting value for that one. And if there's no limiting value, then there's not going to be a sum. Okay, so we're going to say no to limiting value and no to a sum. But you look at number 6, and this is where you're going to start to see that. You can see that we are going to be approaching a number. And it's not always going to be 1 like it was in our other example. So when you look at these terms, it would take us a little bit, but if you started to add some of these together, we know our S sub 1, of course, is 3. Our S sub 2 is 3 plus -1. Well, that's 2. And then you have to add all these fractions together. And it gets a little messy, but just to let you know, if I added the first 3 terms together, I did that ahead of time and got 7/3. And if I add the first 4 terms, so I need to add on one more term, I need to add the -1/9 to it. Well, that gives me 20/9. Okay, and I start looking at those numbers just to see like what are those? It's a good idea to look at the decimals of those numbers. And I'm gonna keep track of those on my graphing calculator. So I got a 2.3, and then 20 divided by 9, yeah, I'm getting 2.2. Okay, well now if I do the 5th term, so I'm adding the 29ths, now I have to add on the 5th term, which is adding on another 1/27 to it. Well, you end up with 61/27. Now let me see what that is going to be. That's 2.259. So as we get closer and closer, if we kept doing this, 6th term, 7th term, you're going to sort of notice that we are going to be approaching about 2.25. That is what we would call limiting value, and then that would be the sum of the infinite series. So I would say the sum is approximately 2.25 on that. Okay, so there's a difference between the sequence in 5 and the sequence in 6. So you just kind of get used to how they look. Okay, we finally made it to the end. So luckily it's not a lot of practice problems. So I'd like you to try 7 through 14 and check your answers, of course, and then let me know if you have any questions tomorrow when I see you. Thanks so much, everybody. Have a great day.